Hello and welcome to another episode of Cuppa Science, the online show that takes the ordinary, adds a splash of science to make it extraordinary. I am your host, Phil Bell-Young, and in today's show, we are looking to the stars and beyond with Naomi Rowe-Gurney from the University of Leicester, as she tells us how a new super-duper space telescope will help us to explore more of our vast solar system. Plus, special guest and king of science busking, David Price, will be gracing our screens with his award-winning and innovative brand of science entertainment. And finally, we'll be finishing off, as always, with a live questions and answers round from you, our wonderful audience. So make a note of anything that pops into your mind because we want to hear them all. But before any of that, just once again, I would like to say a big, warm welcome to everyone who's tuning into our show tonight from wherever in the world you are. Please keep in touch with us and don't be strangers. Let us know your thoughts, your opinions, your desires, or if you like, your favorite space fact, as after all, this is a space-themed show. You can do this by using the comment section beneath this live video that you're currently watching. Or, if you prefer, you can follow us on Twitter at Pint of Science and use the hashtag Cuppa Science. And we will stay in touch with you throughout the show. Anyway, it is now that time of night where we grab a cuppa, don't forget the biscuits, and let's lift off with our featured guest tonight. She is an astronomy PhD student from the University of Leicester, and her research specializes in the study of planetary atmospheres of ice giants such as Uranus and Neptune. Her work is being used in the preparation for the launch of the James Webb Space Telescope, and as a former teacher, she is also always eager to take part in science communication events, which brings her here tonight to your screens. For your enjoyment, please raise a cuppa for Naomi Rowe-Gurney.
Hi. Thanks, Phil. I'm really excited to be here and to talk about my favorite telescope, which is the James Webb Space Telescope. So not many people know that the James Webb Space Telescope is going to be used to look at objects in our solar system. Most of the press to do with the James Webb Space Telescope is to do with the big questions about astrophysics and cosmology, and looking deep into the universe. Whereas this time, I want to kind of bring it back home a little bit closer and show that we are using Webb to look at our own solar system. It's going to be able to look at things from the gas giants, the things that I do my PhD on, all the way to tiny asteroids and comets. So today I'm going to talk to you about what Webb is, and also hopefully give you some of the questions that it might be able to answer to do with the solar system. Okay. So what is the James Webb Space Telescope? Well, it's an orbiting infrared observatory. It hasn't been launched yet, but when it does, it will have a 6.5 meter primary mirror made of 18 separate movable segments. And it'll also have 4 scientific instruments all housed at the back of the mirror that you can see in that top right animation. It's going to have a tennis court sized 5-layer sun shield that you can see unfolding in the bottom animation. All of that's got to be stuffed into a rocket, and then as it's launched, it then gets deployed and it unfolds as it reaches its home at the L2 Lagrangian point. It's okay if you don't know some of those words. Hopefully, the aim of this talk is at the end of it, you will understand everything that I've just said. So it's big, it's complicated, and it's also the future of astronomy. It's going to be the premier observatory over the next decade, serving thousands of astronomers worldwide. Building it has already been an international collaboration between NASA in the US, the European Space Agency, ESA, including the UK, who had a primary role in one of the instruments, and the Canadian Space Agency. So the easiest way to explain Webb and what makes it so amazing is to compare it to the world's favorite space telescope, and that is the Hubble Space Telescope. Hubble was launched back in 1990. It recently, in April of this year, celebrated 30 years in space. And there's a picture here on the slides showing it being deployed from the Space Shuttle Discovery back in 1990. And since its launch, it's had 1.3 million observations. It's done that many observations for scientists. And it's produced these beautiful images you can see in the slide from Mars, Jupiter, Saturn, Uranus, Neptune, and also their moons. You can see a picture of Europa as well, taken by Hubble. So all of these pictures are taken by Hubble. And it's done amazing, groundbreaking solar system science. It's discovered 5 new moons of Pluto, and it's even observed multiple impacts of comets and asteroids hitting Jupiter's atmosphere. So with the amazing things that Hubble has done, imagine what an even better, bigger telescope can do. So how is Webb better than Hubble? Well, I already mentioned it's bigger, and bigger always means better in telescopes. So the animation here shows the relative size of both of the telescopes. On the left, you've got James Webb with its 6.5 meter primary mirror. And on the right, you've got Hubble, which only has a 2.4 meter primary mirror. And you can see a little person for scale comes up on the video as well. So you can see how huge both of these telescopes are and what an engineering feat it is to put them into space. So with a telescope, when you have a larger mirror, a larger collecting area, you can look at dimmer, smaller, colder, more distant objects. So James Webb is able to do that a lot better than its predecessor. Another reason why James Webb is better and different than Hubble is that it looks in the infrared. So Hubble looked in the visible, so it sees what we see between 100 nanometers and 1.8 microns. So light that we see out of the window with our eyes, mostly. Whereas Webb looks in the infrared. So if we split light up using a prism, then we get a rainbow. And towards the red end of the rainbow, we end up with something called infrared, which is actually heat. So we're seeing heat with Webb. And Webb can see from 0.6 to 28 microns in wavelength. So the video here shows a nebula that Hubble can see in the first picture. So let's wait for it to go around again. So this picture here is from Hubble, and it's slowly going to shift into a Spitzer image that's in infrared. And you can see that we're seeing through the gas and the dust, the cold gas and dust, and we're seeing the hot stars beneath. And that's great for astrophysics, but it's also great for solar system science because in the top right, you can see a picture of Jupiter. The left picture is in visible and the right picture is in infrared. And you can see that we're looking through the clouds now and into the depths of the planet to see how it's moving and what it's made of. So it's very exciting. Because it's looking at heat, we need to keep it as far away from Earth as possible because Earth is really hot and we need to keep it cold. Another thing that we're doing to keep it cold is that massive sun shield. So the huge tennis court sized sun shield is to keep all of those instruments cool so that it can look at heat without any interference. And that's why we're putting it 1.5 million kilometers away at something called the L2 Lagrangian point. And a Lagrangian point is just a gravity well where a spacecraft can hover, or any object can hover and stay in constant communication with Earth as we travel around the sun together. So you can see Hubble is only 570 kilometers away, so extremely close. And the downside to having to put the James Webb so far away is that Hubble, between the launch and now, Hubble has had 5 space shuttle missions to carry out repairs and upgrades. And there's no way to do that with Webb, which makes it quite scary for engineers. But it will be worth it because of the advancements that we're going to get in infrared observations. So currently, what we have to do frequently is choose between finding out information about a planet or an object, like what it's made of, etc., like these spectra from Uranus from the Spitzer Space Telescope that you can see in the top figure. So this is the kind of data that I work with. And my colleague, Mike, he works with images from Uranus that are from the VLT, so the Very Large Telescope in Chile. And this is an example where he can't look at any spectrum when he's looking at these images, so he can't find out any extra information, and I don't have any images. So he's lucky he gets to work with pretty pictures and I don't, which I'm always very angry about. But yeah, but James Webb, excitingly, is going to be able to do both. So we're going to be able to have information and image. And that's going to be using something called an IFU, or an integrated field unit. And this integrated field unit, all it does is it has something called a spaxel, which is a spectra inside a pixel. So every pixel of the image is going to have an associated information spectra for us, so we can find out what each pixel is made of, which is really, really exciting for all the scientists working on Webb. So what is it going to be able to do in the solar system with all of this amazing technology? Well, first off, what are we going to be able to look at with Webb? Basically, most things. Everything from Mars out, we're going to be able to observe. Planets, moons, asteroids, Kuiper Belt objects, comets, all of that stuff. And it's more difficult than it sounds for the engineers to have been able to do this, because for a telescope that has primarily been made to look at distant objects like galaxies, distant objects appear very dim because they're far away. And because they're far away, they're also, they appear stationary in the night sky. So you don't have to move the telescope around to look at it. Whereas everything in the solar system is moving relative to us very quickly. And it's also very close, so it's extremely bright. So engineers had to overcome these obstacles to make solar system science possible. They had to make sure that Webb could track these objects moving quickly, and they had to make sure that they didn't break when they look at something bright. So one of the brightest and fastest objects in the night sky that Webb can look at is Mars, because it's so close to us. And we're able to look at Mars only every 2 years or so when it's at its dimmest. So that's really exciting, because even in those short periods that we can look at it, we can do what other telescopes can't do. We can make global maps of Mars, like the example one shown on the screen. Things like water, methane, and other organics. We can use this to help to answer some of the really important questions about Mars. So what happened to its ancient lakes, oceans, rivers? Could Mars have hosted life? So everything always comes back to life and where it came from. So we're always looking for evidence of it. And another exciting thing that it can do is report Martian weather. So back in 2018, there was a global sandstorm that covered the entire planet. And it's important for us to be able to predict and understand these things if we're going to send humans there ever. We wouldn't want to ever get stuck in a global sandstorm. So further out into the solar system, we have the giant planets. So Jupiter and Saturn are our biggest, brightest ones, and we can still observe them with Webb, with most of the instruments. And we can look through the atmospheres, like I said before, to see what they're made of, to see what the weather is like and why it's like that and how it circulates. And we're even targeting specific storms, like the famous Jupiter's Great Red Spot. We're going to be looking directly at that to see inside it and see how it works. We're also going to be looking at the rings of the planets. All of these images here are from the Very Large Telescope in Paranal in Chile. so ground-based observations. So the James Webb observations are going to be so much better than these, and we're going to be able to see the rings even better. But this bottom right-hand picture of Uranus is one of the first ever observations of Uranus rings at these wavelengths, and these wavelengths are the ones that Webb is going to be looking at. And the ice giants especially are some of the main science objectives for James Webb, because we know so little about them. We haven't been back to the ice giants since Voyager 2 in the late 1980s. So there's too many questions even to put on the slide about the ice giants. Basically everything we need to know about them. And it's not just the planets that we're going to be looking at. We're going to be looking at their moons too. The moons of Jupiter and Saturn especially are some of the most interesting bodies to look at in the solar system. Europa, for example, contains likely the second largest reservoir of accessible liquid water in the solar system after Earth. Both Europa and Enceladus, we think, have these subsurface oceans, so deep ocean worlds where we think maybe there could be life. We don't know. It could contain life. And we need to answer these questions by using Webb to characterize their surfaces. And also, not just icy and ocean worlds, there's also Saturn's moon Titan, which is one of the most interesting objects that Webb will look at, because it's the only body in the solar system where there are rivers, lakes, and oceans like on Earth, but they're made out of methane instead of water. So this image here is actually from Cassini, and it's an infrared image, just like the ones that Webb will capture. And remember, when we're looking at infrared, we're able to penetrate through the thick atmosphere of planets and look deep into them. And in this picture, you can see it's revealed the surface, and Webb will be able to do the same thing. So there's also primitive bodies, so asteroids, comets, and Kuiper Belt objects, near-Earth objects. They're of huge scientific interest because they're the leftovers from the formation of our solar system. Asteroids and near-Earth objects like Eros in the video are faint, they're very small, they're very cold, so they're hard to observe, but Webb can observe them. And they contain answers to some of our biggest questions. They can help solve mysteries of the early solar system and planet formation, and maybe these bodies even brought life to Earth, so they can answer where life on Earth came from. And some of you may have heard of Neowise over the last few weeks, a comet that's visible now from the Northern Hemisphere and hopefully visible until the end of July. I'm still waiting for the weather to be good enough to see it. I haven't seen it yet. But Webb is going to be able to look at comets like this and be able to characterize them and tell us more about them. Another form of primitive body are Kuiper Belt objects, or KBOs, otherwise known as a trans-Neptunian object, or TNOs. These are asteroids. Asteroids are mostly in the asteroid belt between Mars and Jupiter, but these KBOs are beyond Neptune in this donut-shaped Kuiper Belt. And they're much colder, they're much further away, which means they're much harder to observe. But Webb is going to be able to characterize every known Kuiper Belt object discovered to date, which is really exciting. And you might think you don't know any Kuiper Belt objects, but Pluto is a Kuiper Belt object. And also one of the largest moon of Neptune, Triton, is also thought to be a Kuiper Belt object. So Webb is going to be looking at these deep, dark, cold places in the solar system. Something else Webb can do is look even further away and also help solar system science. So exoplanets are just planets in solar systems in our galaxy, in other solar systems. So Webb's going to be able to look at exoplanets directly, like the video shown. This was taken over 7 years using the Keck telescope in Hawaii. And the Webb images are going to be even better than this because we won't have to look through the atmosphere of the Earth. And the questions that we answer with this exoplanet science, with our solar system science, will help with answering these exoplanet questions as well. So it's a win-win for both departments. So I wanted to round off by giving a status of the James Webb today. So we're currently, this is a picture that was taken this month. It's currently sitting at Northrop Grumman in California, undergoing testing. So its electrical testing has been completed now, and acoustics and vibration tests start in August. And once it's ready, it will be placed on a special ship and sailed to French Guiana, where it's going to be launched from the ESA spaceport in an Ariane 5 rocket. And remember, it's getting stuffed inside that Ariane 5 nose cone, and that's what it's going to look like when it's all folded up in there. And excitingly, last Thursday, so good timing, there was an announcement that the new launch date is going to be Halloween of 2021. So only a 7-month delay due to COVID-19, which is extremely hopeful. And after it launches, it's going to take around 2 months to reach its L2 Lagrangian point orbit and then cool to operating temperatures, followed by about 4 months of alignment and calibration before the proper science can start. Our team at Leicester is actually, it has guaranteed time to observe all 4 giant planets within the first 12 months of operation, thanks to Heidi Hamill. Also, special thanks to Heidi for providing some of the graphics for these slides. And I'll leave you with some fun links here to learn more about the James Webb. So remember, the UK is a lead in building one of the instruments, the instrument MIRI, and you can learn more about it on their website. And NASA always has great websites for both solar system and Webb. So follow me on Twitter for updates on James Webb and Ice Giant Science. And yeah, thanks to Phil and the rest of the Pint of Science team for having me. I'm looking forward to your questions.
Ladies and gentlemen, once again, Naomi Rowe-Gurney. Thank you so much. That was incredible. I was actually going to ask, so I know we're going to be doing a questions round in a bit, and we've got a short 5 or 6 minute break before we're doing that. And if you do have a question, leave it in the comment section beneath this video. But just before we go, I know you've come out on your talk with a lot of amazing space facts, but do you have that one go-to favorite space fact that you maybe bring out on special occasions or at parties? Anything to let people know that you are the astronomer in the room?
Oh my gosh, when I mention that I'm an astronomer, people just give me a strange look and then walk away usually. My one fact is probably that the ice giants haven't been visited since the 1980s, because people can't believe that we haven't been to them. They just assume they just missed that news. But no, we have not been to Uranus or Neptune since 1986 and 1989, which is crazy. Before I was born.
It is, yeah, that is quite weird. I just assume we are going there all the time, but because I'm not necessarily always looking up space news, that I don't, always find out the amazing things we've discovered lately. But actually, that's a really good point. Mm-hmm. So once again, if you have any questions for Naomi, leave them in the comment section below. We're going to say bye for now, and we'll see you in about 5 to 10 minutes. Brilliant. So before we move on, let's have a quick look at what's been going on in the comments section. So first of all, we've had here, good evening from Ipswich. Good evening, Christian. How are you doing tonight? We've had quite a few people. Actually, we've got people from all over the place. Greetings from Clun Valley. Clun Valley sounds lovely. What's the weather like in Clun Valley? The weather is currently not very great in Hull. As Jessica L will know, hello from Hull. She will vouch there are grey skies all over the place. And good evening from Edinburgh. Good evening, Leslie. Thank you for coming to the show. We have another point someone has brought up here, Heather Hanger. I missed the start. Don't worry. If you've missed any part of tonight, you don't need to worry, because these videos get uploaded to YouTube straight afterwards. So you will be able to catch up at another point. We've also had a couple of comments on Twitter. Jennifer has said that she's got her coffee sorted, but now the important question, which biscuits to add? Ooh, that is a tough question. Which biscuits did you end up going for? Just Jennifer, if you're still watching the show, would love to hear what biscuits you're munching down on. So please do keep the comments coming in. I do love this one. Yay. I'm not even going to try and say that. Well, you know what? I will try and say it, but it's probably not going to go well. Enceladus. Please let me know if I said that right or wrong. Please do keep these comments coming in and any questions that you have. Plus, if you have your favorite space fact, do let us know. But for now, we're moving on to our halftime act. And I'm actually rather excited to be introducing our special guest tonight. He is a recipient of the Manchester Science Festival Josh Award for his outstanding innovation in his highly entertaining and hugely mobile brand of science communication. He is an international performer and trainer at the Science Made Simple, who is dedicated to the grassroots communication of science. Ladies and gentlemen, please welcome the inspirational science busking legend, David Price.
Thank you very much for having me, people. Thank you, Phil. Thank you, Cuppa Science. My name's David. Some people call me David Price. Some people call me Science Busker. I work for Science Made Simple, and we've got a great job around the UK, around the world. What we do is try and get people to fall even more in love with science, technology, engineering, and mathematics. It's a great job, and we love doing it. And I suppose my specialism in science communication and communicating science is this thing called science busking. What is it? Well, it's using the skills of street performers. You know, those incredible people that you see in town hall centres and all over the place, attracting large audiences with their juggling skills, or maybe the magic. Well, we don't use juggling so much and not so much magic, although there's a great deal of science in both of those. But we use their skills to tell science stories that people will desperately want to listen to and participate in. And that's sort of why I'm here tonight. And I've got a sciencey sort of a question for you. Do you think, using science, that I can get this here mobile phone inside this here balloon? Using science, mobile phone inside a balloon. Now, bit of participation. If you think I can, give me a nice big thumbs up. I can feel you doing it through the internet. Nice big thumbs up. If you think that I can't, give me a nice big thumbs down. And if you're not sure, or you don't care, give me some thumbs in the middle. Excellent, excellent. And just, I mean, this is virtual, but just to make sure that this is a perfectly ordinary mobile phone, there's no trickery going on here. Madam, could you just test my mobile phone? Just hold it. Yeah, that's a mobile phone. Lady over here says it's a mobile phone. It's fine. Yeah. And sir, could you just test my balloon? I'll just hang it over here. So it's okay. So it's definitely a balloon. Yeah, thumbs up. It's definitely a balloon. Mobile phone inside a balloon using science. If you're going to try this at home, and we really hope you will, it's very easy to drop your phone when you're practicing. I did it several times. So if you're going to practice this with a real mobile phone, then make sure you're going to do it over something soft. Your settee, a cushion, a nice soft chair, or even maybe when I was learning, I used a piece of wood about the same size as a mobile phone. So it wouldn't matter if I dropped it. Now here we go. Mobile phone inside a balloon using science. World exclusive. Never been seen on the internet or YouTube or Cuppa Science before. 3, 2, 1. Mobile phone inside a balloon using science. Look, your phone's grown something here as well. But I could, through the internet, I can hear you asking me something. You're saying, David, can you turn it around? We think you know how you did that. Okay, well, I've got to unplug my mic here for a second so I can. I just turned my phone around. You asked me to turn my phone around, and I turn it around. What's that? Oh, you want me to turn the phone around? Why didn't you say so? There you go. Oh, there you go. I just turned my phone around. You asked me what to. You want to see the back, right? Okay. There you go. There's the back. You have to see the back. What? What? You want me to move my hand? Right, there you go. I move my hand like crazy now. Is that okay? Is that helping? Wrong hand. Oh, this hand. Right. Mobile phone. Inside a balloon. Using science. Now, I applied a force, didn't I? I pushed here. On the phone, I applied a force onto this balloon made of a rubber material, a very elastic material, while I let the air out of the front of the balloon, out of the hole in the balloon here. So the balloon sort of collapsed around the phone. Now, do try that, but like I say, be careful with your phones. But did you see that before I did that, I got you to participate with your thumbs? And you see, street performers know that if you get your audience to participate early on, as you're telling your science stories, they're far more likely to stay around and buy into that story and fall in love, maybe with your science. Also, did you see that I did something that street performers love to do? I handed my props out to the audience. If you do that, you leave your audience with the props and they're not going to walk away. Okay, some people might, but mostly they hang around. They want to give them back to you. And so you've made a little audience. And street performers know very well that once you've grown a small audience, it's far easier to make that a bigger audience, turn 2 people into 10, 10 people into 20, 20 people into 100. That's the way it works. And we can all use these skills that street performers use to help people fall in love with our science stories. Your family, your friends, your community, so we can get to appreciate our scientific world even more. Thanks, people. Love your science.
Gentlemen, the amazing David Price. That was amazing. That was so funny. I was trying to play along, but I forgot to actually pick the phone up, so it just ended up around my hand. That was utterly incredible. It was amazing to watch you as well. As I've said to you a few times, I'm a science busker as well, and I learned how to do it by following all the guidance that you've written many pamphlets and how to do it guides. So it's absolutely amazing to have you on the show. Just in case anyone in our audience is eager to see more, do you have anything coming up that our audience can tune into? Any opportunities for them to see you again in action?
There are. That's a very timely question, that, Phil. Because I got up extremely early this morning rehearsing for the virtual Singapore Science Festival. Now, fair enough, that's taking place in Singapore over July and August. But in actual fact, anybody can watch in. Anybody can join that link to go and have a look. And our very first show for them is this Sunday morning. Now, of course, Singapore and the UK work on very different timescales. So the show will actually be broadcast at 7 a.m. UK time. But if you follow that link, you'd see a beautiful little, about a 40-minute show on the incredible science of water.
And What about because I know you were saying earlier as well that with your work with Science Made Simple, you've also got a summer school coming up.
And again, very, very timely. In early August, from Monday the 3rd of August to Friday the 7th of August, we've actually got a virtual summer school running, so people could come along to that. I think it's something. What I'm better work at what the timings are. 1 p.m. to 5 p.m. but there are breaks in that. It's a joint project between Science Made Simple and Living Maths, who are a science communication company from South Africa, and we've put together a fantastic program of really, really participative, can-do, make and take science. And we're gonna. It's a space. There's things like a space station challenge. Seeing the invisible, so the electromagnetic spectrum and things like that, and making the craziest musical instruments that have a strong scientific link that you possibly can. And there's still spaces available on that. If you're interested, if people were interested in signing up on that, then follow the link and have a see what you.
I might have to do that myself, to be fair. I've just posted those links directly into the comment section. So if you didn't see the link pop up long enough to write it down whilst it's on screen, don't worry, it should be in the comments, and it will be in the video description of the YouTube video after the show as well. And who knows, we might even tweet it as well. So just once again, thank you so much for coming on our show today. It's been amazing meeting you, and it's been amazing watching you put a phone in a balloon. Just blown away by it. So we're going to say bye for you for now. Thank you once again, ladies and gentlemen. David Price.
Thank you, people. Thank you.
Right. Well, I hope if any of you have been trying this at home, please do tweet us a photo of your phone. I mean, it might be difficult to tweet a photo of your phone if your phone's in the balloon, but if you can get anything in a balloon, please submit a photo to us on Twitter. You can do this using hashtag Cuppa Science. So just quickly looking at the comments, we're getting loads of questions in. This is going to be absolutely amazing, but there was one that jumped out at me, and it is, of course, from our audience with the tweet. With the biscuits, what biscuits did you have, Jennifer? It was blue ribbons. I don't think I've ever had a blue ribbon biscuit before. I'm gonna definitely have to Google those. And we've got as well a space fact. Now I'm going to bring the space fact as from Alex Avery. Favorite space fact: there is an estimated 2 trillion galaxies in the universe. In our galaxy, the Milky Way, there is an estimated 1 billion stars. Space is just jam-packed with stuff. It is. Well, that's probably a best way to reintroduce our featured guest of this evening. So, ladies and gentlemen, please re-welcome to the live feed, Naomi Rowe-Gurney.
Hello.
Hello. How's it going?
Yeah, good, thank you. I enjoyed that science busking.
Yes, I'm just looking at my desk and just thinking, how many things can I now put into balloons? I'm limited by only the number of balloons I've got, so I'm very much looking forward to that.
I have 0 balloons, so going on Amazon to get some.
So we've been getting loads of questions in for you tonight, so we're just going to jump straight into these questions, see how many we can get through in the time that we've got. And there's just been so many good ones. I'm just going to start from the top, and we'll try and work our way down. So starting off with P. Kovacic. Sorry if I've said your name wrong. I really do apologize. How can Webb tell us what the planet's atmosphere is made of, just based on wavelengths?
Yeah, that's a good question. So spectroscopy is where you split up the light into these different wavelengths, and then depending on whether like how much light there is in each wavelength, we can tell what something is made of. Because if there's not much light, it might be that some of the light has been absorbed by a certain element or particle. molecule. And then if there's more light in that wavelength, it might be that something has emitted that specific wavelength. And by looking at those patterns in a very complex like computer program, we can try and piece together what something's made of and what temperature it is.
So it's kind of like you just get loads of information and it's piecing together the puzzle. Very much like Sherlock Holmes.
Yes, incredibly like that.
Is it a relatively, I say relatively, is it quite straightforward, or are there times where you think maybe it's really nice sunny beach weather, but actually it's just storms?
It's pretty complicated. The piece of technology that does it is kind of like a black box that you don't bear to look inside. It's kind of programmed in Fortran and kind of scary to look at. So you just kind of plug things in and make sure that they work by other means, but not by actually touching it. You don't want to break it.
So another question we've had from Sarah Hui, do you know what will happen to the Hubble after the launch of Webb?
Yes, actually, people are really excited that because Hubble has had so many repairs and upgrades, they think that Hubble is going to be able to last until into the 2030s, which is incredible, like crazy good. And so there's going to be crossover between the two telescopes. So with Hubble looking at something maybe like Jupiter in the visible, we can then look at it in the infrared using Webb at the same time, and then we can find out even more information about the planet. So it's going to be really, really exciting to use both at the same time.
So it's not just going to be ending up as space garbage. It's something that's going to be there forever. Can they be used together at the same time, or is it you'd have to use one on one space and then wait for them to get back, because they move through space, don't they? They're not stationary.
So Hubble, you have to submit. It will be serendipity if you can get it so that it will focus on the thing that you want to look at specifically at exactly the same time. So there may be like hours out, but you can still look at the same, let's say, storm on Jupiter as it's rotating into and out of view. You can still look at the same thing relatively at the same time. Sometimes you'll be able to do it so it's exactly at the same time, but rarely.
Well, keeping with the telescope, Anthony Hancock's asked, how will the Webb telescope get from its initial Earth orbit to the L2 point?
Great question. I don't know which kind of propulsion it's using, but it will just propel itself to that point, and then most of the fuel it's going to be using to slow itself down so that it actually stops at that point. Because remember, everything in space, if you don't apply a force to it, it will just keep going. So a lot of energy will be used to bring it back to zero. So then it slots into that nice gravity well.
This is a really good question here, actually. I'm actually wanting to know the answer to this very much as well. What are you most looking forward to finding out about using this telescope?
Well, I mostly work with the ice giant atmospheres. So as I said, with the ice giants, literally all the questions are unanswered. So I'm mostly excited to look at why Uranus and Neptune are different colors of blue. So nobody actually knows why Neptune is much bluer. Also, people don't know why Uranus is so much colder than Neptune, even though Uranus is closer to the sun than Neptune is. There are so many things you can talk about between the two planets. We know nothing about ice giants, where they came from, or why these two in our solar system are so different from each other.
Because that's what your research actually focuses on, isn't it? The ice giants in our solar system. Is it mostly focused on Uranus and Saturn, or
Uranus and
Neptune? Sorry, or do you look at other ones around?
I focus on those two because the data that I'm using from the Spitzer Space Telescope is specifically of those two planets. But some of my colleagues, they look at Jupiter, and they look at Saturn as well. And a lot of people look at exoplanets as well. So you can do the kind of stuff that I do, but with other objects.
Okay. So Colin has asked, well, he started off by saying, great, informative and interesting talk.
Thank you, Colin.
And asked if you could briefly talk about the MIRI instrument. Am I saying that right?
Yes, MIRI. So it's the mid-infrared instrument, and it's going to have a spectrometer and an imager on board. So it's going to be able to take these beautiful pictures that I told you with this integrated field unit, and then be able to look at each pixel and be able to look at these wavelengths and see all of the information. So it's going to be amazing. The UK led the development of MIRI, and so the PI is a lady called Gillian. She is in the UK, and yeah, it's just going to be probably the most important instrument on Webb, because it's the one that's focusing in those mid-infrared wavelengths, which is the ones that we really can't see very well from Earth because of the atmosphere blocking everything.
Okay. Man, I'm learning so much tonight. I literally just thought it was just a big telescope, like the ones you can buy in stores. It's amazing to find out that all these additional gadgets that come with them. I say gadgets. It makes it really underestimates.
They're basically very, very expensive gadgets.
So Gabrielle has asked, how are we going to maintain and update Webb, and ultimately one day dispose of it safely? And I guess this kind of links back to that question of what happens to, because we know we've got all the space rubbish floating through everywhere. So what eventually does happen?
I actually have no idea what happens to space junk. I think that it's one of those short-sighted human things where we kind of just do something and then think about the consequences afterwards, unfortunately. But with Webb, we won't be able to maintain it or fix it because it's going 1.5 million kilometers away. That's 4 times the distance from Earth to the moon. So it's really, really far away. So we're fingers crossed everything works properly. Because remember, when Hubble went up, they had to send a load of astronauts to fix it because the mirror was misaligned because they didn't factor in the temperature changes correctly. So those kinds of mistakes aren't going to be acceptable with Webb. So that's why it's taken such a long time to get it right.
Wow. Yeah. Well, it sounds like it's a very, as you say, expensive gadget. So we want to be extra careful. We've had another question from Sarah. So you talked about the Webb also being able to look outwards to see planets and objects at the outer edges of the solar system. Given the sensitivity, can we also look inwards towards Mercury and Venus?
So it's the sensitivity that means that we can't look at Venus and Mercury because of the sun. The sun is a really big deterrent from looking anywhere in that direction. That's why we put it at our L2 point, so we're constantly looking out into space, into deep space. Because what happens when you face something towards the sun is it heats up. And if we're looking in these heat wavelengths, then you end up saturating all of the filters. And sometimes if you saturate too much, you end up breaking all of them. So if Webb was to turn around, it would just break instantly.
Right. So is there any way, are there, because I guess with Mercury being closer, are there telescopes that we have that are already capable of looking at those from Earth, or is there sort of a space telescope in the works that might be able to focus more inwards?
I think because you don't always have to look directly towards the sun. So some telescopes can look at Mercury, Venus, etc., as long as they're not obviously in front of the sun. It's just because Webb is in this infrared window that we have to keep it cold. Like extremely cold, so we can't even entertain the idea of looking at something so hot.
So we've had a question here, which I think is kind of similar to a question we've already been asked, but it's from Jen. Hi, Naomi. I was wondering if any specific research hypothesis you are hoping to test in that first year of observations, or are they purely exploratory?
So my research is actually looking at the longitudinal variability of Uranus, especially right now, and also some of Neptune as well a little bit later on. So what I'm looking at is how Uranus changes as it spins. So what we want to see is what's happening to the clouds and the composition from one side of Uranus to the other. And we see with Spitzer a lot of variation between for Uranus between one side and the other, but not a lot for Neptune. So we want to understand why that is, and the only way to actually understand is to have these spaxels from James Webb, and to be able to pinpoint exactly where these changes are taking place on the surface in the atmosphere.
I think we have time to squeeze one more question in, and I think this is kind of a good question to end with, and it is from Alex. Who is James Webb, and why is the telescope named after him? Also, how long do you think it will be the leading space telescope?
Okay. The James Webb is named after the a NASA administrator. So basically just a powerful white guy from America. I really don't know. As usually things are named after them. And what was the other part of the question?
How long do you think it will be the leading telescope?
I hope for a long time. I mean, considering I think it's meant to last at least 5 years, but they predict it to last a lot more than that. I mean, usually they have a very low predicted runtime, and then they go on for much longer, as happened with Spitzer. The same thing happened with Cassini. So we just have to hope that it will last for as long as possible.
Yes,
without the ability to go out there, though, it's definitely got a finite time.
Well, hopefully it'll last longer. Hopefully we'll get as much from it as we can. What I am going to do now, we are running out of time, so we're going to have to stop the questions. But I mean, there's been so many questions. It's actually been quite hard to go through and pick them all out from the comments. So what we're going to do, would you mind if people contacted you via Twitter to ask you any more questions? If they've got anything, any burning questions they want to ask, we'll bring it up onto screen now. So there is your Twitter handle. So any questions or any comments, any statements, and there's been loads of really nice things as well. Like people have been saying, that they can't wait to see these images from the web.
Same.
We've had someone, Jennifer again, who said that she's very much the research area that she'd love to join in. Again, I'm trying to find all the lovely comments, but there's just so many questions in every single one. But I think this sums it up really, really nicely. Great talk. Can't wait to see the results. And it has been an absolutely phenomenal talk. We're going to bring up your name and Twitter one more time, just for people to take that down. Please do go follow Naomi to find out all the latest stuff, I guess, that you tweet on your profile about your research, everything that's coming out, and any questions that we didn't have time to answer today. And just from me and the rest of the Cuppa Science team and the Pint of Science team, just thank you so much for coming on our show today. Ladies and gentlemen, please once again, massive round of applause to Naomi Rowe-Gurney.
Thank
you. Just once again, thank you to both our guests. That was just amazing. And as I said, the comment section is just blowing up. There's so many amazing questions I wanted to ask. I almost wish we had more time to go through every single question, but unfortunately, this does bring us to the end of our show today. There has been one thing that I've seen come up here about blue ribbons, which I'll bring it real quickly. Blue ribbons. I always thought it was blue ribbon. Did I say it wrong? Can't believe I was today years old when I found out that it was blue ribbon. Oh, not a clue. Not too sure myself either. Again, lovely comments and the final last comments. Thank you. Yeah, it's just been amazing, and I think I will bring these all up because this video does get uploaded to YouTube afterwards, and I think it is just amazing to have so many incredible speakers come on to our wonderful show. So thank you. Thank you again so much, Naomi, for your talk. And in fact, thank you to both our guests tonight. So that is our show. A massive thank you once again to Naomi from the University of Leicester and to David Price from Science Made Simple. And again, a massive thank you to you, our wonderful audience, and the Cuppa Science production team. Without you guys, we wouldn't have a show, and it's been so amazing having a show. Join us again next week join us again next week when we're going to be going down under to discuss a pandemic response, or a good response, or the best way to respond to a pandemic with medical consultant Dr. Andrew Stein. Plus, we are joined by special guest